We are now in the fluid and electrolyte thing, and this is over on this table is on page 1020 in your books, okay? Now, with the rest of this chapter, I believe you're going to see that you already know this. So that's kind of cool, I would hope. So, sodium. Let's talk about sodium. Sodium's role is, for one thing, it does a lot of things, but for one thing, it is the #1 cation that exerts osmotic pressure in the extracellular fluid. In other words, it's the one outside the cell that's drawing water. And that makes sense because you know the sodium potassium ATPase pump is busy pumping sodium out of the cells, right? So it's extracellular. It's controlling your extracellular fluid volume. Okay, it's where water goes. Because remember our mantra, right? Water follows sodium and other solutes. Okay, so with our balance of it, you remember the whole aldosterone thing. I know you do. And I know you know that Renin-Angiotensin-Aldosterone System. I know without a doubt in my mind that you have this. Is that right? Thumbs up? Okay. All right. So remember, when my blood volume drops, or my blood sodium content drops, or my blood pressure drops, or my potassium concentration goes up in the extracellular fluid, that's going to trigger that whole renin-angiotensin-aldosterone system. We are going to release aldosterone. We are going to tell the kidneys to suck in sodium. Do you remember which part of the kidneys we tell to reabsorb sodium? Which part of the nephron? Nope, not the
tubules.
In the kidneys.
Distal convoluted tubules.
Okay, the distal convoluted tubules, and a little bit the collecting duct. And then when we're bringing in the sodium, who lets water follow sodium?
And other solutes.
And other solutes, yes. Who lets the water follow the sodium? Who lets the water in?
Renin?
Nope.
ADH.
Yes, ADH. ADH lets the water follow the sodium. So we're working on the distal convoluted tubule and we're working on that collecting duct. All right, cool. Okay, so we've already looked at aldosterone, so we should be pretty comfortable with that, I'm thinking at this point, because I feel as if I've flogged you with this stuff. Do you feel a little flogged with it? Okay.
Maybe.
All right. Okay, good. Another thing just to add in with this whole regulation of sodium is the cardiovascular system has those baroreceptors. And we actually remember the carotid and aortic sinuses are the pressure receptors. And they're the ones who say, you know, if my blood volume goes up and my pressure therefore goes up, because if you've got more fluid in the pipes, you've got more blood, higher pressure, right? So then those aortic and carotid sinuses, baroreceptors, get stimulated, which then talk to the hypothalamus, which is king or queen, depending on your gender identity of all, which then sends the sympathetic nervous system to talk to the kidney. Now, so if my pressure is too high and sympathetic talks to the kidney, am I going to vasodilate or am I going to vasoconstrict the afferent and a little bit the efferent arterioles going into the glomerulus? Which would it be? We would dilate, exactly. Tell me why. You're right.
To lower blood pressure.
Okay, but why does it work? You're right, it does. But why does it work? When I dilate those arterioles into the glomerulus, why would it increase or why would it drop the pressure? Because that's what we're trying to do.
Because there's more space.
It makes it slower. GFR gonna be rise.
It does make the glomerular filtration rate go up. Why?
Because it slows down the flow.
No, it increases the flow through, right? Mm-hmm. If I dilate, I've opened up my hose, remember?
Oh,
so I've got more fluid going through, right? So now it's going to squirt out. So I'm going to make more urine, right? And the sodium will go out in the urine with the water, We also have, of course, from our heart itself, remember atrial natriuretic peptide?
Okay, so it's dilating, it's making it bigger, so it's making it move through faster. So it's not actually withdrawing as much out of what fluid is being pushed through.
It's increasing the pressure in the glomerulus, so it's pushing more fluid through. It's a pressure diuresis is what this is. So it's just that same thing as, you know, when I was saying, when you turn open the tap and you've got the soaker hoses in your garden and all of a sudden they're shooting out geysers. If I vasodilate the arteriole, then what I'm going to do is increase the pressure in the glomerulus, which is going to force more fluid out. It's a pressure thing. My glomerular filtration rate goes up and I'm going to produce more urine, because it's back to that conveyor belt, you know, with that Lucy and Ethel thing with chocolates, and the faster you go, the more shoves go through because you can't do what you need to do and grab it back. That includes the water. I'm shoving more stuff through. It goes through faster and I'll lose the sodium. And the other thing that I can have from the whole cardiovascular system, besides that pressure diuresis where the sympathetic nervous system vasodilates, arteriolar, I've got the atrial natriuretic peptide, which its job, if it's natriuretic, what's happening here?
Pressure, decrease blood pressure.
It does decrease the blood pressure, but how? What's that word natriuretic mean to everybody?
Because it inhibits the Renin-Angiotensin-Aldosterone.
Easy for you to say. Yes, it does. It inhibits the release of ADH, of renin, aldosterone, all that good stuff. So that word natriuretic is actually saying sodium in the urine, right? And then we go back to our water full of sodium and other solutes, right? We also have ADH. ADH certainly has a role in this. So if I have a high pressure, I have a high volume, will I increase or decrease my ADH? My pressure is high. More or less ADH?
Less.
Yeah, lower it, less, right? And if my pressure goes low, then I want more ADH. And if I have low sodium in my plasma, then I would need low levels of ADH, right? If I have high sodium, I need to dilute it, so I would have more ADH, so I add more water in. Does that make sense?
Yes.
Right? With me? Okay. All right. There are other things that affect sodium balance. And one of them, we'll talk about the boy and girl hormones, but the estrogens and progesterone are interesting because, and this, we'll see this when we get into talking about female reproduction, but estrogen is similar to aldosterone. So girls, and there are a lot of girls in this group. So girls, think about this. When you go through the menstrual cycle, right, you've got those days where you're just puffy and bloated, and guys, watch out, because when girls are in this phase, when the estrogen levels are high, you're increasing more sodium absorption. And so therefore you have more water on board, which is where you get that puffy person, and which gives you that my clothes don't fit, I'm all bloated, I don't like it, don't mess with me phase. Okay. But then progesterone, when those levels rise, when you get to that phase of the ovarian cycle, then progesterone actually blocks the aldosterone effects on the renal tubules. And so therefore now we don't reabsorb as much sodium. And so now sodium goes out and the water follows it. So that's when, you know, the clothes fit better again and the attitudes get better too. Okay. Make sense? They're not the primary control of sodium, but it is happening. And it kind of explains that bloat versus then I pee it out and then I bloat and then I pee it out. It's that cycle that goes on until you get old and shriveled and hit menopause. We also know that glucocorticoids will increase reabsorption of sodium because remember, one of the features of the glucocorticoids, which are made in the zona fasciculata right next to those mineralocorticoids, is that you increase your reabsorption of sodium. You have edema with the glucocorticoids. Your pressure goes up as well as your blood sugar levels. Okay. So that's the story of aldosterone, of sodium rather. Well, aldosterone too. I keep hitting on aldosterone. Okay. So now it's time to talk about, oh my goodness, with this whole blood pressure maintenance thing. So when we're talking about all these things and putting them together with our sodium balance, this is a beautiful chart. It's in your books. It's over on page 1023. So everything that we just went through is in here. So if my blood pressure drops, you can see my afferent arterioles are saying, oof, you know, I don't have enough pressure. Okay, because we did the high pressure. So what happens is we decrease our filtrate concentration of salt in our ascending limb of the loop of Henle. So what happens is the kidneys release renin, right? Because your pressure is too low. So when they release the renin, then angiotensinogen that the liver made turns into angiotensin 1. How did we become angiotensin 2? Angiotensin converting enzyme in the lungs, ACE. Okay, then we did the two things. We did the vasoconstriction and up comes the tubes are tighter. So now the pressure goes up, and we did the whole stimulate the adrenal cortex to release aldosterone, to go to the distal convoluted tubules to make me reabsorb more sodium. And who let the water follow?
ADH.
Yes, ADH. Okay. So ADH lets the water follow the sodium and your blood volume goes up. So does your pressure. Ooh. And if my pressure is dropped, my baroreceptors are saying, oh my, the pressure is kind of low. Oh dear. And that's the aorta and the carotids, those sinuses are saying, oh dear. So the sympathetic nervous system is going to talk to the kidneys. So what will we do to the kidneys, to the arterioles going into the kidneys if my pressure is low? Do I vasodilate or do I vasoconstrict?
Constrict.
Yes, because if I slow the flow, then I get more time to reabsorb everything. I reabsorb my water. So now I've got less of a loss in my urine. So I've got more volume in the pipes. And so therefore, woohoo, I increase my blood pressure. Oh, that's right. And of course, in order to let the water follow my posterior pituitary, that ADH, though, did the posterior pituitary make that ADH? Nope. Who made the ADH? Hypothalamus. You guys got it. Perfect. Okay, so then the ADH is released by that posterior pituitary or neurohypophysis and talks to those collecting ducts and says, hey, let the water follow the sodium. Woohoo. Isn't this just a most wonderful chart?
Mhm.
All right. I think this was a very good job. All right. So anyway, so next I want to talk about potassium, and that's not going to be in there for me. So I'm just going to talk about potassium with this chart. Ready? Here we go. So we backed up a little bit. Okay. And we're back to that table that was over on page 1020. So potassium, what do we need potassium for? Well, it's really important for maintaining our cells' resting membrane potential. So that's a big deal. We need it for buffering. One of the things we'll do in the world of medicine is we will mess with the potassium levels in order to affect the pH. Okay, so the potassium is really important in making sure that we can do muscle contractions of skeletal muscle, cardiac muscle, the neurons firing, because that whole sodium, potassium, ATP, ACE pump, maintaining that resting membrane potential, the buffers, because we can do a hostage swap out with potassium and protons. So that's a really good thing to know when you're having somebody who's doing really poorly and they're very acidotic. I can say, well, let's swap out potassium for protons and see if we can ditch some protons and bring in the potassium. Okay, so that's a big deal. The other thing is how do we regulate it? Well, if you know what we do with aldosterone for the sodium, potassium is just exactly the opposite, right? So if my potassium levels are low, what will aldosterone release do? Increase or decrease?
Increase.
Sure. Remember, it does the opposite of sodium.
It decreased.
So when I have low potassium levels, I will have lower aldosterone levels. When I have high potassium levels, I will have higher aldosterone levels. Does that make sense? Just if you know the sodium, potassium does the exact opposite, which fits in really nicely with the way that sodium and potassium move with the sodium-potassium ATPase pump, okay? So aldosterone, again, is really in charge of what potassium does. All right, ready to move on to calcium. So I'm going to stick with this table. So we're still on page 1020. Calcium. When you think about calcium, one of the first things you should think about is, where do we mostly store our calcium?
Bones.
Bones, absolutely. So it's with calcium and phosphorus together. Calcium phosphate is hydroxyapatite. It's that matrix of bone. So it's not the only thing calcium does, as you know. Where else would you think of calcium being really important?
Muscles.
Absolutely. Muscle contraction. We cannot contract our muscles. And there are two things that go with that calcium role with muscle contraction. One is you need it for pulling the troponin to pull the tropomyosin to expose actin and myosin binding sites. But that calcium is important in membrane permeability, right? Because that's that whole, remember, like with the heart, we had the calcium channels keeping us depolarized inside. So we had a you cannot put me into a tetanic contraction ability. It's also important with neurons. The ability to secrete neurotransmitter is a calcium dependent activity. You can't clot your blood. Remember, calcium keeps showing up in that whole pathway of coagulation. So calcium does a lot of stuff. Now, who are the two hormones that control it?
Thyroid hormone and parathyroid hormone.
Yep.
Okay, calcitonin and parathyroid hormone. So calcitonin does what to blood calcium levels? Raise or lower?
Calcitonin down.
Down. It lowers it because it stimulates those osteoblasts to build bone and it inhibits the osteoclast. Okay, so how does parathyroid hormone work?
The opposite.
Increase.
The opposite.
It increases.
Increases.
And how does it do it?
It stimulates osteoclast.
Osteoblast.
Okay, it stimulates osteoclasts and inhibits osteoblasts. Does it do anything else?
Yes, it does. On your kidneys and on your GI tract, you have
It
to
does.
release, I don't remember right now, but a hormone to absorb more calcium. So it works on your kidney and your GI tract also.
Yeah, so with this, you're exactly right, Thais. So the small intestines, we stimulate the kidneys to activate vitamin D. Vitamin D then increases the absorption in the intestines of calcium. And kidneys just reabsorb it, don't send it out if I need to get it higher. So that's why, remember, a parathyroid hormone gets that higher billing and, oh my goodness, regulates calcium metabolism. Well, that's not fair. Calcitonin matters a lot. You need it to build your bones, but you also have more things that you hit with your parathyroid hormone, okay? All right, then we've got magnesium. So, and everybody see the terms, because hypercalcemia, hyperkalemia, hypermagnesemia, hypernatremia. Everybody okay with the terms? Because calcemia makes sense. Kalemia is what? Which of these?
It's potassium.
Potassium. Natremia.
Sodium.
I heard
Sodium.
yes. Okay, so make sure you're comfortable with those, because nobody is going to say, hypersodiumemia. They're going to say natremia. Okay, all right. So with magnesium is really an important regulator in metabolism and carbohydrate and protein metabolism. If magnesium gets out of whack with your heart, it'll throw it into a lethal rhythm. We call it torsades. So there's a lot of need for dealing with the magnesium. But as far as how we regulate it, still a little bit of a just the kidneys are doing it. Okay. There's no hormonal control of that at all. The other thing that we have to care about, is the regulation of the anions. So let's see, one of these. So the calcium, what you want to think about, or calcium, the chloride, chloride, all you want to think about for chloride regulation is wherever sodium goes, they're married. It's a partnership. So chloride tends to want to go where sodium does, all right? That's why, like in that loop of Henle, in the ascending limb, when we're reclaiming sodium chloride. They tend to stick together, all right? That's your table salt stuff. Okie dokie. Good so far? All right. Bicarbonate, we're going to talk about, we've already mentioned that because we looked at it with the respiratory system, right? But we're going to talk about it big time with the buffer system now, all right? So it is an anion, and it is important in the extracellular fluid. As a matter of fact, your plasma, your blood plasma, has what we call the bicarbonate reserve. So we're going to look at that one, all right? So when we get to the pH balance thing, all right, chapter 2, chemistry, everybody's favorite. When you look at acids and bases, there is a big difference between a strong acid or a base and a weak acid or a base. Strong acids or bases, when you put them in water, they completely dissociate, okay? So hydrochloric acid, the stuff you have in your stomach, it is a very strong acid. Your stomach has a pH of 1 to 2 when it is empty. It is why if you vomit empty stomach acid up, it burns. Now, when we look at the carbonic acid, it is a very weak acid. So the rule is weak acids and weak bases are fantastic for buffering because they are very happy to pick up or drop off either the protons or the hydroxides. Okay, so these guys are what we use big time. We also use potassium for buffering, but when we're talking about our big pH control, what we really tend to focus on is this bicarbonate ion. And that was really what you guys were looking at when I gave you that flipped classroom assignment of pH balance, okay? All right, so when we're looking at the whole process of our tubular reabsorption of bicarbonate, this gets really hairy looking. So luckily, what I really need you to get is some of the basics of it, and that doesn't include all of this stuff. Some of it we have already seen. Remember this from the respiratory system? Because remember one of our other mantras was carbon dioxide plus water equals
Acid.
Acid.
That's right. Carbon dioxide plus water equals acid. All right. So that's a lot of what they're showing in here. All right. Now, what I want to talk about is how are we dealing with acid-base balance? So here's the lecture that you wanted before I made you do the assignment. All right. First off, just in general, pH. Remember that pH is a reflection of the number of protons. The lower the number, the more the protons, right? Everybody okay with that concept? Because it's what we call a negative logarithmic scale. So in other words, when we say something is a pH of 1, what it is it's saying that it's 10 to the minus 1 of protons. If we say something is a pH of 7, our physical chemistry neutral number, then it's saying that we have 10 to the minus 7th protons. Okay, so pH of 10 is 10 to the minus 10th protons. So the bigger that little super fixed number up there, these fewer the protons. Everybody cool with that stuff? Yes? So pH of 1 means 0.1 protons. pH of 2 is 0.01. okay, and so on. So the bigger the number in pH, the fewer the protons, the lower the number of protons. All right, so when we look at pH and we're looking at these protons, what we're looking at is all these things that depend upon our body being in the right pH range. Because if you remember how things are held together, we've got ionic bonds, we've got covalent bonds, which holds, you know, like glucose is held together by sharing bonds. And then we've got those hydrogen bonds, which are that those kind of unequal charge distribution where you get, you know, the folding of the proton chain or the rather the peptide chains to make a protein. So if you have the wrong pH, it starts interfering with those hydrogen bonds. And when you interfere with hydrogen bonds, things fall apart. And I mean that in a literal sense, okay? So our enzymatic reactions are pH dependent. We have to have our normal blood pH being between 7.35 to 7.45. Absolutely, that's our range that we need. And it's a number range you'd better know because it will be asked. I know because I wrote the tests. Your normal intracellular pH is 7.0, which is perfect in between, all right? So we get most of our protons from metabolic processes. So remember, like our ketone bodies, keto acids, lactic acid, all these things, we get these protons and we have to manage them. All right, and we do this with our weak acid, weak base molecules, and we do it with our proteins. So alkalosis versus acidosis. When you look at alkalosis in general, anything that is above 7.45 is truly alkalotic. But what I want you to always remember is that when you have 7.35 to 7.45, 7.4 is right in the middle of that. So to be really fully correct, anything that's lower than 7.4 is on the acid side. Anything that's lower than 7.35 is an acid state. Anything that is above 7.4 is on the alkalotic side. If it's above 7.45, you are in alkalosis. We good? So that 7.4 is our tipping point between acid side and alkaline side in the world of our blood plasma, okay? So we're working with these chemical buffer systems. So bicarbonate buffer system is the extracellular fluid buffer system. It does buffer intracellular fluids also, but it is the #1 buffer system for the extracellular fluid compartment. So that's our plasma, that's our interstitial spaces, okay? All that stuff. Think bicarbonate. When your pH drops, in other words, you get extra protons, what happens is the bicarbonate ions of sodium bicarbonate will grab up our protons and become more of the carbonic acid. And if you need to, if your pH goes up so that you don't have enough protons, then it can go the other way. Carbonic acid will be pushed over to dissociate and release the protons and have the bicarbonates left behind. Does that make sense to everybody? So far, so good? Okay. Alrighty. So now, when we talk about the alkaline reserve, this is our pool of available bicarbonate ions, okay? The amount that we have in our alkaline reserve, our pool, is actually regulated by our kidneys, okay? Carbonic acid is constantly being made by carbon dioxide because carbon dioxide plus water equals acid, right? But so respiratory is controlling the carbon dioxide part, that acid part. The kidneys, the metabolic, is regulating that bicarb. So we always have bicarb is the metabolic, is the kidneys. Carbon dioxide is the acid, is the respiratory system. Okay, everybody okay with that? Sound familiar? Okay. All right. We do have a phosphate buffer system. It's important in your intracellular fluid compartment. It's important in urine. It's the same kind of idea. It's a sodium phosphate system. But what I'm going to focus on is more what proteins do to pH regulation and what the bicarbonate does, okay? So with proteins, when you look at a protein molecule, it's huge. It is made up of a lot of amino acids, each of which has their individual little rest of the molecule that gives them their name, whether they're leucine, isoleucine, phenylalanine, whatever. But when you have this chain of all of these individual beads of amino acids, what you have is this huge possible buffer thing. So these proteins are called amphoteric molecules. Amphoteric means I can swing either way. I can either be an acid or I can be a base because I'm huge and I got all these parts, okay? Sort of like an amphibian, a frog or a toad can go both water and land. So an amphoteric molecule can act as either an acid or a base. It just depends upon the pH. It's why, looking back at the GI tract, when we ate protein and it got to the stomach, it raised the pH of the stomach, which would stimulate the G cells to release gastrin, to stimulate the parietal cells, to increase production of the hydrochloric acid, to drop the pH back down. So proteins are really great for acid neutralizing, okay? All right, so when we talk about the whole process of respiratory acidosis and alkalosis versus metabolic acidosis and alkalosis, what I want to do is do examples. So does everybody have something with which to write and on which to write? Because if you don't, get something. Okay, we're going to do some problems together. You ready? Okay, so let's see. Let me get here. I'm telling you what to do, and I'm not even ready myself, so how rude am I? All right, get some paper myself. So I go through this. All right. Okay. Remember, case. All right. Okay, so let's do, okay, how about if we have, everybody ready? I'm going to do pH, carbon dioxide, and bicarbonate. I'll do it the same way each time. So here we go. I've got a pH of 7.23. Everybody got that? 7.23. What do you know about it?
It's
High, low, or normal?
Low.
Low.
Acidosis.
It's low, so I already know a part of the name, right? Acidosis. So I've got acidosis for sure. Okay, so the carbon dioxide level is 51. High, low, or normal?
very high.
Okay, that's high. Okay, so we know that's up. So who's controlling that? Is that respiratory?
Respiratory.
It's respiratory. Okay. So then I look at this bicarb. So 23, is that high, low, or normal?
Normal.
It is normal. Okay. So if that's normal and the respiratory volume or the respiratory control of carbon dioxide says it's too high, what is my problem here?
You're breathing your lungs.
Okay. So I have a respiratory acidosis would be its name, right?
Mm-hmm.
Is it compensating or not? So when I'm asking about compensating, I'm saying, is the one that's not the cause of the problem trying to help or not?
No.
So the way to know is it normal? It's not trying to help, right?
No.
Okay. So if it's normal, it means it's not trying to help. It means that this is uncompensated respiratory acidosis. We good?
When do you say it's partial?
Okay, so let's change these. I can change one number and make it partially compensated. So if I say I'm partially compensated, my pH is still not in normal range, but both of them are out of whack. So give me a different number for my bicarb that would say it's trying to help. Take
40.
that 23. What does it do?
It would rise.
It would rise. Perfect answer. So maybe I would have to take it to say 28, right? Because that would be up and out of normal range, right? So that would tell you that I have partially compensated respiratory acidosis. Now, how would I make it fully compensated? Change one number and make it fully compensated.
Make your pH normal.
pH normal.
Perfect. Make your pH normal. So it would be 7.36. You'll never make it to 3.4. Okay. Our body has a philosophy of we'll get you into the appropriate range, but I'm not going to overshoot because that's just crazy. So the rule of this is if you have your carbon dioxide and your bicarb are both out of whack in the same direction, one is compensating for the other. So then you look at the pH and say, well, is it high or low, right? Is it above or below 7.4? If it's above, it's an alkalotic issue. If it's below, it's an acid issue. So then you need to look at, well, who's going to cause that? Okay, so let's look at, let's say, let's do another one, okay?
Well, Professor, if
How
I might
about,
ask,
sure.
I did a little bit of personal research because I was having trouble finding which specific one was correct in that instance. It was hard to say who was at fault. And I did find the anagram of Rome. Respiratory is opposite, metabolic is the equal, essentially, that they're both going the same direction. Is that applicable, or is that just something randomly found?
No, that's a great, it's a great little memory device. Okay. And what it is, I mean, if we were together, I'd be drawing on a board, but unfortunately that's just not going to work. So when you look at the effects, write down, if you have carbon dioxide, just put down carbon dioxide. If it goes up, draw an arrow up, okay? If carbon dioxide levels go up, what does that do to pH? Up or down?
Down.
Down. If carbon dioxide levels go down, what does that do to pH?
Up.
Up. Okay. Take bicarb, HCO3 minus. When bicarb levels go up, what does it do to pH?
It goes up.
Makes it go up. If it goes down, what does it do to pH? Makes it go down. Okay. I'm seeing pointing downs. Okay. So therefore, when you look at these, Rome is a great idea. Okay. Respiratory is going opposite. Metabolic is the same, equal. Okay. Sometimes I have to work, if I have to work too hard at a memory aid, then it's not a good memory aid for me.
It was just what I happened to find. I was unsure because when I actually did the test, it said two of them, I followed that and it had different answers, but it was one of those, it could have gone either way if you didn't know that. And so I was interested to see what you had to say about it, if it was accurate or not. So
here's the thing. If you've got, so let's see, how about if I have, let's try this one. You ready? Let's do this. 7.36 is the pH. Carbon dioxide is going to be 26. And bicarb is 16. Okay. So tell me, pH of 7.36, high, low, or normal?
Normal.
Normal. But is it on the acid side or the alkaline side of normal?
Acid side.
Acid side. So I put a little parentheses acid to the side. Okay. So then I say, okay, so I've got it's normal, but on the acid side of normal. So then I look at the other two values and I say, are they normal also? Because if they're not in the 35 to 45 for carbon dioxide and 23 to 26 for the bicarb, then I'm not normal. I'm not okay at all, but I'm compensating, and I am fully compensating because I am now in the normal pH range. So now I look at this and I say, okay, so carbon dioxide of 26, high, low, or normal?
Low.
It's low. Okay. And bicarb, 16, high, low, or normal?
Low.
Low. Okay. So now I'm saying, okay, so that carbon dioxide, what would it do to pH? When you have a lowered carbon dioxide, what does it do to pH? Raise it or lower it?
Raises it.
Raise.
It raises it. Because less carbon dioxide means less carbon dioxide plus water equals acid. So there's less acid, so therefore the pH goes up. That's that opposite thing from Rome. Okay, the bicarb, if it's lowered, what does that do to pH?
Making it
Lowers.
It lowers it. So you see that the two effects would go opposite. So in this case, I have something on the acid side. Who is in charge of in this particular one with these numbers, which one is the cause of the acid state? Is it the carbon dioxide or is it the bicarb? Who made the pH
It's the
drop?
bicarb.
Bicarb.
Sure, the bicarb made it drop. So that then puts this squarely on the metabolic part, doesn't it?
Yes.
Okay, so I have a metabolic acidosis and my little carbon dioxide is trying desperately to fix it. Okay, so let's talk about this for a second, okay? So if I have fully compensated metabolic acidosis, let's talk about how we got there, okay? Metabolic acidosis, that means that I have too much acid left and I've lost bicarb. Would you agree? The numbers are showing that, correct? Okay, so how would I lose bicarb? Well, I tell you what. Diarrhea would be a great way. I lose bicarb when I have the runs. So you get some poor sod who's got diarrhea going on and they can go into metabolic acidosis. What's another way to have your bicarb levels drop, be in a metabolic acidosis state?
Vomiting.
Say it again.
Vomit.
Not vomiting, that's going to get rid of your acid and put you in an alkalotic state. That's the exact.
Peeing a lot?
What?
Peeing a lot?
Nope, it's not about peeing. Oh, people, come on. It's all about that blood glucose thing, and we're using our gluconeogenesis. Diabetes mellitus, ketoacidosis, right?
Yeah.
Right? That's a way to get to metabolic acidosis, is that you're in ketoacidosis, whether it's starvation, it's diabetes, mellitus, one of those things, right? We good? So what is this person who is in metabolic acidosis that's being compensated for fully by the respiratory system? What do they look like? What's their respiratory rate like? In order to get rid of that much carbon dioxide, what do they look like?
They're breathing really fast.
Yes, they're blowing off carbon dioxide. Does that make sense?
Mhm.
Okay. All right, let's try another one. Okay, let's do a pH of 7.45. High, low, or normal?
Normal.
Normal, but
Alkaline.
alkalotic side. So I'm putting alkalosis with a little parentheses around it because I'm not sure. Okay, so and then I've got my carbon dioxide is 49. High, low, or normal?
High.
No.
High. Okay, my bicarb is 29. High, low, or normal?
High.
High.
High. Okay, so I have alkalosis in parentheses. I'm in normal range. So who is causing this? What does this elevated carbon dioxide do to pH? What does 49 do to pH? Up or down?
down.
Down. Am I in an acid issue here?
No.
No, respiratory just got off the hook for being the problem child, right? Instead, it's the rescuer. So then we look at the 29 in bicarb. What does that do to pH?
Increase.
It does. It increases it. So now I know who's at fault and I know who the fixer is. So what do I call this? Give me the whole name. What kind of compensation?
Fully compensated.
Fully compensated.
Metabolic. Alkalosis.
Alkalosis. Awesome. Okay, so this is somebody who maybe is vomiting, or maybe they have an NG tube and we've been sucking out their stomach contents. Bless their hearts, we did this to them. Maybe this is that little old lady who figured out that she won't mess herself by peeing because she has decided to dehydrate herself. Oh, and that's right. She also came in with way too much sodium bicarb, because what did she do? She had upset stomach too. Remember we talked about this lady? And so she is now in a metabolic alkalosis state because she's loaded up with sodium bicarb, baking soda for upset stomach. All right, so those are ways that you can end up this way. And so if we're trying to hold on to our carbon dioxide, what does the breathing look like in metabolic alkalosis when you're compensating with the respiratory system?
You are breathing it slowly.
You're not breathing as much. Okay, right. Slowly, shallow. So here's the thing. When we are compensating, the respiratory system is a really quick fix because you can, or you can hold on, right? But it has a limit to how much it can actually compensate, simply because, yes, you can blow off carbon dioxide or you can retain it. But there's this other piece of respiration called oxygen. So can you hold your breath for a really long time to build up your carbon dioxide levels to compensate for metabolic alkalosis? No, because you need the oxygen. So respiratory system is a quick fix, but it has a limited range of fixing. All right, bicarb. Bicarb has a wide range, but it's slower. Okay, it's just a slower thing. So when you have a respiratory problem, it takes a longer time for bicarb to fix it. Okay, so let's see. How about, all right, I've got a pH of 7.35. Okay, high, low, or normal?
Normal.
Okay, normal, but what are we putting in
Or
parentheses?
acid.
Acid in parentheses. Okay, so 7.35. Carbon dioxide is at 55. High, low, or normal? High. Okay, bicarb is at 27. High, low, or normal?
High.
High. Okay, so what is going on here? What have we got?
Metabolic.
The carbon is pH lower, but the bicarb is pH higher. So therefore, that would be metabolic. No?
Fully compensated respiratory acidosis.
Bingo. Fully compensated respiratory acidosis. Okay, so let's break it down again. So 7.35 is in the normal range, but it's at the bottom of the normal range. So it's on the acid side of normal, correct? Everybody agreed with that?
Mm-hmm.
Carbon dioxide, we all agreed it was up, and we know that that does what to pH again?
It makes it lower.
Makes it lower, drops it, exactly. Bicarb, if it's at 27, that's high, right?
Right, so it
Not very high, but it's high. So what does that do to pH?
It brings it up.
Brings it up. So you've got a problem that's on the acid side of normal. The only one who would cause the acid in this case is respiratory.
It's respiratory. Okay.
So it has to be a fully compensated respiratory acidosis. Now, these are crazy numbers that I'm making up, okay? So it's not reflective. You would have a much higher bicarb level. You would see this with a COPDer. Okay, somebody who is relying on their hypoxic drive, their carbon dioxide levels are chronically elevated, so their protons are chronically elevated, so they're always in an acidotic state, but the bicarb, the kidneys have been compensating. So that's how it is that these people can live, because you can't have a pH that stays out of whack and be okay, because your enzymes start to unfold. Things do not work when the pH is out of range. You mess with all those hydrogen bonds and you don't work. Okay? Everybody cool? Make sense?
I have one question. What does acute mean?
Acute is fast. Remember when we talked about the leukemias?
Yeah, I remember, and that's what I thought. It was like fast onset or something. And but when I was doing my research for this assignment too, I kept coming upon acute metabolic, and I didn't know what that means. What does that mean? Is that
Means
part of
it happened fast. For instance, if I have the flu and I just puke my guts out, or I got food poisoning and I'm puking my guts out, so I'm losing a lot of acid, then I would go, that's an acute metabolic alkalosis problem.
Does that have anything to do with compensation?
Well, the compensation is what's your respiratory rate doing to help fix the metabolic issue.
Okay.
Okay. So whatever is screwed up, the other one is going to be the compensator.
Okay.
Okay. So that's why you're always looking for what do they do? You look at each one every single time. You go through the same steps every time. Okay. Make sense?
So even though the carbon dioxide is unbalanced and compensating, as well as the bicarb compensating, you automatically will look at the pH to determine whether or not it's acidosis versus alkalosis, which determines if it's respiratory versus metabolic.
Absolutely.
Okay.
Well said. So all I'd have to do, and the problem we just did, is take my pH and instead of 7.35, make it 7.45. And then I would blame the metabolic system, and the respiratory is trying to fix it. If it is a metabolic overdue, if my bicarb is at fault for alkalosis, then I know that it's going to be on that upper side. And if the pH is in normal, but it's in the normal range, but it's on the alkaline side, I'm looking for which one of those did it. No, it's not always metabolic. In this case, it is. All I got to do, I look at my pH. I always start with pH. Am I in range?
Higher, lower.
And am I above the 7.4 or am I below it? So I'm determining acidosis or alkalosis. Am I in range or not? It doesn't matter immediately. I know that I'm not okay if I'm outside the normal range on either side. Okay. But whose fault it is determined by looking at the carbon dioxide and looking at the bicarb and saying, what would they do to the pH based on what direction they have gone? If carbon dioxide goes up, we know that shoots the pH down.
Correct.
If carbon dioxide drops, it shoots the pH up. With bicarb, the ME of that Rome thing that Michael had, with metabolism, if it goes up, pH goes up. If it goes down, pH goes down. So all I've got to do is I look at my pH and then I say, okay. So I look at these values down here. And if my carbon dioxide is up, I know it's dropping the pH. Is my pH problem on the acid side or is it on the alkaline side? If it's on the acid side, I'm going to blame respiratory. I look at the bicarb. If it's down and pH and the carbon dioxide is down, and the pH is down, I'm going to blame the metabolic system because dropping the value of bicarb is dropping the pH. Okay. The biggest thing is to remember if both of them are going out of range in the same direction, one is compensating for the other, then you look at who would move that pH in that direction, either up or down. Better?
I have a question. When we say both, are we talking the carbon dioxide and the bicarb? Or
yes, ma'am.
Okay.
Compensation is about both carbon dioxide and bicarb moving out of range in the same direction. Okay.
Okay. The same direction?
Yes, they're going to move in the same direction because they have the opposite effect on pH.
So if carbon is up, it's moving pH down. So your bicarb should be down to move pH down. That's in the same direction, correct?
The individual pieces of what you said are true, but no.
Okay.
All right, listen. If I have, let's just say, Let's make it straightforward where everybody's all is normal, okay? If I have like a pH of 7.38, okay? If my carbon dioxide is 44, is that high, low, or normal?
High.
High, low, or normal? Quick.
Normal.
Normal.
Normal. Bicarb, if it's 26, high, low, or normal?
High.
Normal.
Normal.
No,
I
that's
thought it was
not
22 to 26 was normal for bicarb.
Right, so 26 is
Exactly.
normal.
It's
Oh, I thought you
normal.
said 27.
Well, I thought I said 26. My mouth may not have said what my brain thought it said. 26 is normal. That would be a normal ABG, right? So if I wanted to turn it into something else, I could say, well, if I have because I can have a normal pH and have everything out of whack. Everybody's good with that, right? Because I compensate, right? That's fully compensated. What if I had, let's see, let me make something here. How about 7.44 for a pH? Okay, so we're looking at what are we putting in parentheses because it's not 7.40, it's 7.44.
Alkalotic.
alkaline.
Okay, alkaline. Okay, so we've got a little parentheses. I'm normal, but I'm on the alkaline side of normal. So then I say, okay, well, my carbon dioxide is at 50. High, low, or normal?
High.
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 Say hi.
My bicarb is at 35. High, low, or normal?
High.
High. Okay, so now we go through the steps. We've got our alkalosis in normal range. So we already know, and we looked at these two, they're out of whack, and they're out of whack in the same direction, correct?
Correct.
Okay. So we know one is compensating for the other because they're both out of whack in the same direction, up, right?
So the carbon dioxide is compensating.
Yes, for the
Awesome. Okay, I understand
bicarb,
that. Okay.
because the elevated bicarb will cause the alkalosis problem.
And because the one is different, and then okay. I think I get it.
Okay.
All right. Thank you.
You're welcome. Okay. So for these different problems that we can have, all right. So because we're going to finish up this little bit of this chapter, we're almost there. We'll get to the rest of it, I guess, tomorrow, or I mean Thursday. But the thing to know is that if you look at a person and just you can look at when you look at these ABGs and you have expectations for what these people look like. If you are in respiratory acidosis, so you've got too much carbon dioxide, right? And your pH is down. I'm expecting that my kidneys are going to start raising my bicarb. Would you agree? So I could end up in respiratory acidosis by being an asthmatic and have a sudden asthma attack where I'm building up carbon dioxide because I cannot do gas exchange because my bronchioles are closing down. All right. Hopefully we'll intervene before my kidneys have to go fixing my pH because I also have an oxygen issue, right? If I have a panic attack, have you ever heard of anybody saying, breathe into a paper bag with a panic attack? Okay. So when you look at a panic attack, the reason for breathing into a paper bag is because what do you do when you are having a panic attack? What's your respiratory rate look like?
You hyperventilate.
You hyperventilate. So I'm
More
blowing out all this carbon dioxide, right? So if I put on that paper bag, I will breathe back in my carbon dioxide. Okay? So there are things that I look at. If I am a COPD or I have a chronically elevated carbon dioxide level, but I can't live that way forever because that would be not okay to be in a low pH all the time. I would not survive that well. So my bicarb levels will rise because my kidneys are going to compensate. I will be in a fully compensated respiratory acidosis state. That's your COPDers. Okay, so we've kind of done the metabolic acidosis versus alkalosis. We've looked at respiratory acidosis, and respiratory alkalosis is that panic attack. And we put that bag on. Okay, does that make sense? Because it's kind of cool stuff to get. And I will tell you, I teach this to critical care nurses in the past, and you'll be ahead of that game. Everybody good? Does this make sense? Okay. All right, so let's see. I think I'm just looking through these problem things. I believe we're okay with this, this system. How do you feel about ABGs? ABG be me. You guys got this. That's very exciting to me because I know that this is a concept that kind of is hard for a lot of people, but it sounds to me like you're getting there.